So let's look at the use of nuclear chemistry in medical applications. So, describe the use of radioisotopes in medicine. All right, so right here they're using a scanner to detect radiation from a radioisotope that is accumulated in an organ. They are pointing at her thyroid and shows the accumulation of radioactive iodine-131 in the thyroid. That's what we're seeing all through here. So radioisotopes with a short half-life are used in nuclear medicine because they have the same chemistry in the body as they do as non-radioactive atoms, and they give off radiation that exposes a photographic plate or a scan to give an image of the organ. So it basically lights it up, if you will. Not literally, you're not going to be glowing, but the scanner can actually pick up on those isotopes, and you can actually see that organ as well as identify damage. I know that for me personally, I had a CAT scan, and they put in, I think it was thorium, but anyway, into an IV, so they could light up my liver and my pancreas and my gallbladder to kind of see what was going on there as far as functions go. So different isotopes that are commonly used are right here. And the different type of radiation, okay, what will come out. So measuring blood flow to the heart, okay, gamma, postrates, abdominal imaging, tumor detection, gallium, iodine, treatment of thyroid, brain and prostate cancers, iodine for Graves' disease, hypothyroidism, thyroid, prostate cancer. So we can just see these isotopes in the way that they're used. After the patient receives the radioisotope, the radiologist determines the level and location of the radioactivity emitted by the radioisotope. Gamma rays emitted from the radioisotope in the organ can be used to expose a photographic plate, producing a scan of the organ. So here is the woman has been injected with iodine-131, and here is then that picture of her thyroid that comes up as the scanned image. So in positron emission tomography, positrons are emitted from positron emitters such as carbon-11, oxygen-15, and fluorine, and then positrons combine with electrons to produce a gamma ray that can be detected, giving off a three-dimensional image. So it's really advantageous for doctors and medical professionals not just to see a slice of the organ, but actually a three-dimensional image, so they can actually locate, let's say there's a spot of cancer or something like that they can pinpoint where it is and then how to attack it. So right here, positrons are used to study brain functions and metabolism. So mine will probably be like mostly cool blue because that means there's not much functioning going on. You know how it goes. But so we get these images, right? CT scans are directed at the brain in layers. They're absorbed at different rates due to different in densities of body tissue and fluids, and that's what I was going to talk about in a previous section. You know, tissue could mean many different things because there are many different types of tissues and amounts in each individual body. But it does create a three-dimensional image of the brain and any tumors or hemorrhages. For example, I found out, this must have been like 9-10 years ago, I was getting these horrible headaches, and so they did a CT scan of my head, and it actually does turn out I had a brain. And they found out two things. One, that I had a very severe sinus infection, but two, they came across a cyst on my pituitary gland, my pineal gland in my brain. And, you know, they were even able to differentiate the difference between a cyst and a tumor. All right. And don't worry, it's very common. The only thing that it may affect is my sleep cycle or whatever. But hey, it's all good. I don't sleep much anyway. I'm a night owl. All right. So here's a CT scan showing a tumor in yellow in the brain. That is not an awesome thing. Okay. That is a very large tumor in comparison to the brain. But hopefully they'll have caught it, quickly enough that they can do something about it. MRI, which I've also had, which, many of us may have had if we've had ligament injuries, knee injuries, things like that, is based on absorption of energy when protons and hydrogen atoms are excited by a strong magnetic field. This is why you don't wear belly button rings or nose rings or anything that's magnetic when you go into an MRI. The protons align with the field and vibrate, with different frequencies, which can then be picked up by the scanner. And if you're claustrophobic, MRIs used to be this tube that you would go through, but now they have more claustrophobic friendly, where they're open on sides so you don't feel so trapped. So that's some medical uses of radioactive isotopes currently in use today.